Hi everyone, welcome back, and we're going to take a look at the last bit of plate tectonic information that we need to understand. So what I'd like you to do is I'd like you to take your dynamic crust packet and turn to the page that looks like this. It's currently page 21. It's got South America on it, and beneath it it has a cross section of a convergent boundary right here. So locate this, and also please open your ESRT to page 5, the plate tectonic maps. Alright, so let's take a close look at the top task. We have a couple of tasks here that we want to look at. And let's start by looking at the depths of the earthquakes here. Now notice we have a very active earthquake and volcano zone right here along the Chile-Peru trench right there. Big, very active zone. In fact, the most powerful earthquake ever recorded was in this area here. And a lot of volcanoes, very tectonically active, very geologically active area. So what I need you to do right now is go to your ESRT, page 5, and let's start by labeling this tectonic plate, which I've called A, and this tectonic plate, which I've called B. So let's label them right on your diagram and pause the video. Take care of that right now. Okay, so hopefully you found that tectonic plate A is the Nazca plate, and tectonic plate B is the South American plate. So B is the South American plate, which is kind of obvious really because the continent of South America is staring you in the face right there. So now, scientists have the ability to find exactly where earthquakes have occurred, not just how far away, but also how deep inside the Earth the earthquake is happening. And they've noticed an interesting pattern here along this Chile-Peru trench, which caused us to infer a few important things. So the first thing I want you to do is take a look at the depths of the earthquakes in the key. Any earthquake that's within 75 kilometers of the surface would be indicated with a little circle. And any earthquake that's between 75 and 300 kilometers below the surface would be a triangle. And deeper than 300 kilometers deep would be a little square. So we're going to indicate depth with these symbols. So what happens is this. Scientists have discovered that the most shallow earthquakes are the ones that are closest to the trench. So what I'm going to need you kids to do is just draw your little circles along the coast fairly close to the trench the way I'm doing it right here. Okay, so your circles are going to go in this area. You're pretty close to the trench. Alright. So here are the shallower earthquakes. Now in reality, 75 kilometers down is hardly shallow, but the shallowest of the three. Now, earthquakes that are at moderate depth, between 75 and 300 kilometers deep, those are found a little farther away from the trench. And they're going to be indicated with a triangle. So we're going to put our triangles on the other side of the circles, like I'm doing here. So please draw your triangles all the way down. And guess where the deepest earthquakes are found? You know, the deepest earthquakes are found even farther from the trench, like this. All right. So if you do this correctly, you should have something that looks like this. All right. So make yours look good. So now, what can we infer from this? What does this teach us? What does this show us? Well, here's where things get interesting because, you know, we have to look at the evidence when we figure out what's going on out there. That's how we figure out what's going on in the world, is we look at the evidence for these things. So here's my question for you. My question simply is this. As you travel eastward from the Chile-Peru trench, what happens to the depth of the earthquakes? So The question is, as distance from the trench increases, earthquake depth does what? And your answer is that as you travel eastward from the trench, earthquake depth increases. The earthquakes are getting deeper. Now, what can we infer from that? Well, let's take a look. I'll just whip up a little diagram right here for you. So here's the Earth's surface. So as we travel from the trench, let's say the trench is here, as we travel eastward from the trench, the earthquakes appear to get deeper and deeper and deeper and deeper and deeper, like this. That's the pattern. They get deeper and deeper. Now, what does that look like to you? Interesting. Well, let me add to the diagram a little bit. All right, and let me add this right here. Well, what does this look like? This looks like a piece of lithospheric plate subducting beneath an overriding plate. Interesting. So this earthquake data is what tells us that there's probably something called subduction happening here. So let's take a look down here at the cross-section of a convergent boundary. So earthquakes closer to the trench are more shallow. Earthquakes farther from the trench are deeper. Even farther, even deeper. Even farther, even deeper. And I'll tell you, this goes on for hundreds of miles beneath the continent. This is how we have a sense that there must be subduction going on beneath that continent. Because what happens with an earthquake? An earthquake is when something that should be sliding past something else gets stuck. And we can figure that the depth of that contact is getting deeper and deeper. That's how scientists know that subduction occurs at a convergent boundary like this. Okay, I hope that makes perfect sense to everyone. Okay, now a little review. What do we call plate A, and what do we call plate B? All right. Well, I'll tell you what. I'll help you out here. Plate A is the subducting plate. Therefore, plate B would be known as the what? Plate B is the overriding plate. It stays up. And one more thing. Continental crust never subducts into the earth. It stays up the whole time. And that's why it's so much older than the oceanic crust, which is getting recycled every 150 million years or so. The oceanic crust gets pulled into the earth, melted down, and recycled. Continental crust does not get pulled down into the earth like this. Okay, one more thing. I want you to jump ahead a few pages, and we're going to take a quick look at what are known as hotspots. Okay? Now, a hotspot, well, a hotspot's definitely a unique sort of thing. I taught you kids that volcanoes happen along convergent boundaries, but volcanoes also happen in other places known as hotspots. Now I'm going to show you an example here of a hotspot, and I'm sure a little quick animation here. And let me just turn the sound down on it. I don't think you want to be hearing that. And I will add my own narration. So let's take a look. So you've got planet Earth, you've got your cores, and you've got your stiffer mantle. Now what happens here is you get tremendous heat down here in these cores, tremendous heat. And sometimes you have an unusually hot, an area that just kind of ejects some particularly hot material here at the bottom of the mantle. And this mantle material gets, again, really, really hot, and it creates kind of like a pipe, like a tube of super hot material, which flows toward the surface. Now this is not a plate boundary, it's just an isolated tube of super hot material which is going to melt the lithosphere right above it. So it's going to melt this lithosphere, this hot magma plume, this hot plume they call it, mantle plume coming up, super hot material, maybe 3,000 degrees Celsius near the surface. It's going to melt this rigid mantle and this crust right here. It's going to melt it, and the melting is going to produce volcanoes. All right? But don't forget, tectonic plates move. Tectonic plates are in motion. They're constantly moving. Not very fast, but they are slowly moving. So what happens is this volcano, which is active right now because it's got this melted rock beneath it, gets moved away from this plume, and it gets shut off. So this volcano right here is going to be dead. Now, these are active volcanoes right above. But notice, as the plate moves, we have to keep making a new volcano over the hotspot plume right there. So what this gives us is a chain of volcanoes. Older, younger, 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 younger. And this one is so young that it's pretty much under construction right now. And that's what happens. And that's how the Hawaiian Islands formed. Okay? So let's take a close look at what's happening. Tectonic hotspots are the result. Basically, they're places where hot mantle material rises toward the surface right here. And it melts the lithosphere and creates these volcanoes. Okay, now let's take a look and see how many hotspots are shown in the ESRT. It's going to be a little scavenger hunt for you. You're going to have to pause the video when you're ready to do this. So we're going to take a look at the diagram here. Hotspots are indicated with this symbol right here. It's like a little explosion symbol right there. So your job right now is to find how many hotspots there are and put your answer right here. Let's see how you do. Okay, hopefully you've counted them all and you've come up with 8 hotspots. 8 hotspots. You had your Iceland hotspot, your Galapagos hotspot, Canary, Yellowstone, Bouvet, you know, and it just goes on and on. So there's 8, but there's actually more than 8, but the ESRT only shows 8. So now let's apply this to the most famous of all the hotspots is the Hawaiian Island hotspot, which is right down here. So this diagram shows the Hawaiian Island hotspot. We have ourselves a mantle plume, at least 3,000 degrees Celsius coming up here. And let's take a look at the islands that make up the Hawaiian chain. The island of Kauai, fairly far away from the hotspot, is about 4 million years old. Okay, in fact, I'm just going to reveal this all at once. Make it easier for you. Okay, Oahu is 2.5 million years old. Molokai is 1.5 million years old. Maui, popular vacation spot, is 1.2 million years old. And the island of Hawaii is 0 million years old. So the island of Hawaii is currently under construction. It has active volcanoes adding rock to it right now. But remember, the plate is moving in this direction. Okay? The plate is moving this way. So at one point, Kauai was here on the hotspot 4 million years ago, but it got moved out. And then the hotspot created Oahu, which got moved out. Then the hotspot created Molokai, which got moved out. So right now, Hawaii is the one that's currently on top of the hotspot. And one day it will be moved out and another volcanic island will be under construction right there, being formed above that tectonic hotspot. Okay, I hope this is making some sense. All right, in here is where you would indicate the plate movement, the direction of the plate movement. And all right, so thanks for paying us this close attention. If you have any questions, leave them at the end, and we'll be on later. Good job.